In lecture 34, we're going to begin looking at the dot product, which is the first of two different ways that we can multiply vectors together. Now, we have talked about multiplication in earlier lectures involving vectors, but only by multiplying a vector by a scalar, which means to stretch the vector according to some real number scale. So multiplying it by a scalar like the number 2 or the number 1/2 would increase the size of the vector but keep it in the same direction. What we're going to talk about in these upcoming lectures is how do I multiply two vectors together, and what does that actually mean? And so we actually have two different ways to multiply vectors, and the first of which is this dot product. So we're going to learn how to find the dot product of two vectors, and then the dot product will have some applications. So each of the different ways of multiplying vectors, dot product being one, the cross product being the other, have ways of have applications. What actually allows us to calculate the dot product, for example, can allow us to find the angle between two vectors, which then means we can find when vectors are parallel or orthogonal. Orthogonal meaning perpendicular or at a 90 degree to each other. And then we can take any vector and break it down into components. Now, we've done components in the x and y direction, but we can now use the dot product to find components in any direction and then an orthogonal direction to that first chosen direction. We'll talk about that when we get there. So what do we mean by the dot product? So let's take two vectors. We'll call V AI plus BJ, and W is CI plus DJ. Remember, I and J are unit vectors in the x and y direction respectively. A, B, C, and D are just now real numbers. The dot product is denoted by V dot W. So we're always going to put a dot in between the two. That's why it's called the dot product. And it's defined as V dot W is A times C plus B times D. Notice that the output of the dot product is a scalar. You take two vectors and take their dot product, you end up with a scalar value. So just as a way of an example, let's look at what that would mean for these two vectors. In this case, A is 2, B is -3, C is 3, and D is -4. What we're doing to take the dot product, we're going to take 2i minus 3j and dot that vector with 3i plus 4j. We take the x components, multiply them together, so 2 times 3, and we take the y components and multiply them together. Okay, -3 times a +4, and we add that result up. So this becomes 6 plus a -12, which is 6 minus 12, or -6. This scalar right here is the dot product of those two vectors. We'll discuss in a moment what that actually means, but first thing we wanted to make sure we could do is find the dot product of two vectors. To explore some of the properties that the dot product might have, let us consider what would happen if we reversed W and V. What is W dot V? In other words, if I took 3i plus 4j and found the dot product of that with 2i minus 3j, that would be a 3 times a 2, because you're multiplying the x's, and then multiply the y's, you get plus a 4 times a -3. And if you kind of look up here above, notice how all that's doing is changing the order of these two. So as you might expect, the dot product is something that then commutes. You end up with a 6 plus a -12, which is again -6. And because the only effect of changing the order of the vectors changes the order of these multiplications that then you add together, changing the order of real number multiplication doesn't change the answer. So dot products will always commute. Now, what happens if you take a dot product of a vector with itself? So take 2i minus 3j dotted with 2i minus 3j. You end up with a 2 times a 2 plus a -3 times a -3, which happens to be 4 plus 9, or 13. Now, that doesn't seem so interesting until you look at what we have called the magnitude of a vector from earlier introductions to vectors. Do you remember how you find the magnitude of a vector? It would be the square root of a squared plus b squared. So you end up with the square root of 2 squared, right, because that's the v from up here, plus a negative 3 squared, or the square root of 4 plus 9, which is equal to square root of 13. And in looking at these two, what do I notice about these? Well, I notice, and I'll highlight this, the 2 times 2 is this 2 squared right here. And this negative 3 times negative 3 is negative 3 squared. One thing that we can say is that v dotted with itself is the same thing as the magnitude of v, but without the square root, so put a square there. There's a relationship between the dot product of a vector with itself and its magnitude. Okay? In fact, another way of writing it is the length of the vector is the square root of the vector dotted with itself, or we could write it as v dot v raised to the 1/2 power. So there are some properties that we kind of observed earlier in that example, but are true for all dot products. First of all, the dot product is commutative, which is our fancy mathematical term for v dot w is w dot v. The order changes direction. Secondly, not that we've observed this, but it is definitely true, the dot product distributes over vector addition. What I mean by that is it acts exactly as you would expect multiplication to act. If I were to have two vectors added together, say w plus v, that sum is a vector. Let's take that and take the vector u and dot with that sum. Since this is like multiplication, we would expect it to distribute the way that multiplication does. Even though it's a completely different kind of multiplication, you end up with something that does distribute u dot w plus u dot v. That is in fact true for all vectors. A couple of additional properties that are true and not too hard to see why they would be true. We've actually seen the first one. V dotted with itself is its magnitude squared. And if you take the 0 vector, not just the 0 number, but the 0 vector, 0i plus 0j, and dot it with any vector, you get 0. One of the primary applications of the dot product is that it allows us to find the angle between two vectors. In particular, if I wanted to find this angle right here, call it theta, we can get that angle using some trigonometry, basically some triangles that we covered back in the solving triangles section of this course, as well as just an understanding of how vectors work. Now think of, if I were to draw a point right here and extend this vector v in its negative direction. So let's draw negative v right here. And the reason I did that is so that you could see, if I draw, let's do this in red, if I draw this vector right here, that is u plus a negative v, or u minus v, which is exactly the same as this one right here. That is u minus v. So the reason I do all that is, and in fact I'm going to do the magic eraser here. I can erase all of this. Boom, boom, boom. I've made my case now that this vector right here that I've got drawn in red is u minus v. If you put two vectors at the same starting point and you go from the end of one to the end of the other, that's the same thing as the vector that you ended up at minus the vector that you started with. So this vector that extends from the end of v to the end of u is u minus v. And we saw that by drawing this little parallelogram, or drawing the vector v in reverse from the end of u. Now, with that being done, the point now is we've got a triangle. A triangle where the length of this side right here is the magnitude of v, the length of this side right here is the magnitude of u, and the length of this side, of course, is the magnitude of u minus v. And we've got an angle in here that we want to find. Well, guess what that means? We've got, if we know u and we know v, we've got three sides, or a side, side, side triangle. How do you find the angle in a side, side, side triangle? We use the law of cosines. Law of cosines would relate this angle plus these two sides to the opposite side. Namely, we would be able to say that the magnitude of u minus v squared is the magnitude of u squared plus the magnitude of v squared minus 2 times the magnitude of u, magnitude of v, cosine of theta. Now at first it doesn't look like there is anything to do with dot products in here, but we go back to this property that we had above right here and apply that for all of my squares in here. Boom, boom, boom. I can rewrite all of those as dot products. So this becomes u minus v dot u minus v equals u dot u plus v dot v minus 2 magnitude of u, magnitude of v, cosine of theta. And now what I'm going to do is I'm actually going to make use, I'm going to scoot down here a little bit, I'm going to erase part of this line, draw it again so it doesn't pick up so much space, this right here. I want to look at this guy right here. We're going to simplify or expand by the distribution rule. Since there is a distribution property for dot products, then I can say u minus v dot u minus v will behave just like a binomial problem, in that you can take u dot minus v dot u, and minus times minus is a plus. This now all looks like the following. You end up with u dot u minus u dot v minus v dot u plus v dot v. That's what this side right here looks like. And because these are the same thing, by the commutative property, what I actually have is u dot u minus 2u dot v, just combining those like terms, right? Since this right here is the same thing as u dot v, I'll actually have 2 of those minus u dot v. So I have minus 2 u dot v plus a v dot v. So this is all right here on the left-hand side of that equation. All that together implies that u dot u minus 2u dot v plus v dot v is equal to u dot u plus v dot v minus 2 magnitude of u, magnitude of v, cosine of theta. from this earlier equation. Now I've got a u dot u on one side and a u dot u on the other. They subtract out if I subtract that from both sides. Similarly, if I subtract v dot v from both sides, I end up with a minus 2u dot v equals a minus 2 magnitude of u, magnitude of v, cosine of theta. And if I divide both sides by negative 2, the result is u dot v is equal to the magnitude of u times the magnitude of v times cosine of the angle between the two vectors. So here's another way of seeing the dot product. The dot product is also the magnitude of one vector times the magnitude of the other vector times the cosine of the angle between them. Now, realize that in most cases, if we're trying to find the angle between the two vectors, we're going to already know the two vectors. So we know u, we know v, which means we know the magnitude of u and the magnitude of v. What we're trying to find is cosine of theta, so we actually have the equation we need. Cosine of theta would be u dot v over the magnitude of u times the magnitude of v. The right-hand side, we have all the information we need, and the left-hand side is cosine of the angle we're looking for. To find theta, we'll simply have to move the cosine to the other side by doing cosine inverse. This is the form we usually leave our formula in, but that is the formula that gives us the angle between two vectors. So here's the theorem we just basically proved and derived the result for. If u and v are two non-zero vectors, then the angle between them satisfies this formula right here. So let's use that to find the angle between the two vectors. So first I've got to find u dot v, and on the bottom I got to find the magnitude of u and the magnitude of v. So let's start by finding u dot v. I can write it all the way out, but I'm going to start skipping that step. I'm just going to multiply the x components and multiply the y components and add them up. So this is 4 times 2 plus a negative 3 times 5. So that's 8 minus 15, or negative 7. The magnitude of u is this. Oh goodness. Let's get back out of here. Sorry about that. The magnitude of u is square root of 4 squared plus a negative 3 squared, or square root of 16 plus 9, square root of 25 is 5. And the magnitude of v, square root of 2 squared plus 5 squared, or the square root of 4 plus 25 equals a square root of 29. So plug all that into this formula. Cosine of theta is equal to u dot v over magnitude of u, magnitude of v. So cosine of theta is negative 7 over 5 square roots of 29. So theta is going to be the cosine inverse of negative 7 over 5 square roots of 29. And just to be clear, notice that taking the inverse cosine is perfectly legitimate in this circumstance, because where does the cosine inverse give us answers? If you'll remember back when we talked about inverse functions, sine inverse gave us this angle, but cosine inverse gives us outputs of these angles from 0 to 180 degrees, which is exactly what we're looking for when we have two vectors. The angle between them is always going to be between 0 and 180 degrees, because if this vector were to rotate around any further and we end up with something down here, we're going to find this angle, which is always between 0 and 180 degrees. So use the cosine inverse to find that. Plug that into your calculator. And I made sure my calculator was in degree mode. I get 105.1 degrees as the angle between those two vectors. So you find the dot product, you find the two magnitudes, plug it into the formula, take the cosine inverse in your calculator, and you'll have the angle between any two vectors. At this point, it's not hard to see that we have a couple of special circumstances, special angles between two vectors that would be common or things that we would often want to look for. One being when are two vectors parallel, and the second being is when are two vectors orthogonal. Now, parallel means they're going in the same direction. Actually, these two vectors are parallel. I would also claim that any vector going this direction is also parallel because it lies on the same line. Now, if two vectors are parallel, what's the angle between them? Okay, the angle between parallel vectors is either 0 or 180 degrees. So two vectors are parallel if there is a non-zero, if one is a non-zero scalar multiple of the other. And what I mean by that is one is a scaled version of the other. They have the same direction. So how do you tell if they have the same direction? Well, you simply have to look and see, is there a constant factor being multiplied by one vector to get the other vector? Okay, so is V equal to some alpha times W? Now, the only way that would be able to be true, since this is negative 6I plus 4J, and this is 3I minus 2J, is can I find a number that makes that work, right? Is negative 6 some alpha times the number 3, right, from here? And is 4 that same alpha times the negative 2? If I get the same answer both times, then they are parallel. If I get a different answer in each equation, then they're not parallel. What's negative 6 divided by 3? It's negative 1/2. That's alpha, right, in the first equation. And the second one would be, what's 4 divided by negative 2? That's a negative 1/2. That's alpha. Then yes, they're parallel. Of course, another way, if that didn't make a whole lot of sense for you, to figure out if they're parallel would be to find the angle between them. And if you get 0 or 180, then they are parallel. If you look back up above, you'll notice that's more work than the shortcut that I just showed you. All you got to do on this one is, you may see it right here, I'm taking the x components and dividing them, and the y components and dividing them in the same order, and if I get the same answer, then they're parallel. The other relationship that is significant and sometimes shows up in applications is when they are orthogonal. Orthogonal is another fancy word for what you've probably heard before as perpendicular. Orthogonal is used in more advanced mathematics because we can talk about orthogonality in other contexts besides just lines and vectors. Perpendicular is usually only in reference to geometric shapes like lines and vectors. But we say they're orthogonal or perpendicular if the angle between them is 90 degrees or pi over 2 radians. And recall that this is the formula that relates the angle between two vectors and the vectors themselves. If theta is equal to 90 degrees, then cosine of theta is 0. So the question is, if this whole thing equals 0, then when is this fraction right here going to be 0? And the only way for that fraction to be 0 is if the numerator is 0. So the quickest way to check if two vectors are orthogonal is just to check, is u dot v equal to 0? Because if that's equal to 0, then this fraction is equal to 0, which means cosine of theta is 0. And the only way for cosine of theta to be 0 is if theta is 90. So two vectors are orthogonal if their dot product is 0. We can demonstrate that two vectors are orthogonal by simply taking their dot product. So u dot v in this case would be 2 times 3 plus a negative 1 times 6, right? Because that's The y component is -1. That's where I got this right here. So you get 6 minus 6, which is 0. Done, which means u and v are orthogonal. The last application that we're going to look at is how we can take one vector and decompose it into two orthogonal vectors. Instead of breaking it into its components in, say, just the x and y direction, we can find two other vectors that are orthogonal to each other and find how much of the vector x in parallel to one and how much of the vector x in parallel to the other. Okay? So this is called decomposing a vector into orthogonal components. We did an application with vectors in an earlier lecture where we had a block on an incline. Gravity was acting on the block straight down, right, parallel to this, perpendicular to the ground, which is straight across. In order to determine the force it would take to move the block up the incline, or the friction that is generated by this block, we need to know this component right here. So we basically need to find the component of this vector in a direction that is parallel to the top edge of this incline. And by finding this one, we might also want to find what is the force that's going straight down or perpendicular to that vector. So we want to find these two vectors right here. Again, taking the vector for gravity and finding out how much of that force is acting in the direction parallel to the incline and how much of that force is acting straight down against the, straight down meaning perpendicular to the incline itself. So how do we decompose two vectors, or sorry, one vector into a component parallel to one vector and then orthogonal to that vector? Let's talk about that. We consider two vectors, a v and a w. Our first goal is to project v onto w. In a direction that is perpendicular or orthogonal to w, I'd like to drop a line straight down that forms a right angle with w. I would like to know, and maybe I should draw this in red so you can see it a little bit better. I would like to know, what is this vector right here? If I were to call that v1, what is that vector in the direction of w? Secondly, we can then think of v as the sum of two components. So by going perpendicular straight up as high as this vector right here, if I were to call that vector, which again is perpendicular to w, call that v2, then v is equal to v1 plus v2, where v1 is in the direction of w, or parallel to w, and v2 is orthogonal to w. So just for consideration, let me point out that then v1 has to equal some scalar multiple of w. Now, why is that the case? Well, it comes back to what we said up here. In order for two vectors to be parallel, one is going to be the scalar multiple of the other. The second thing I want us to observe in this case is that because v2 is orthogonal to w, what is v2 dot w? Well, it's 0. So I'll put these two pieces together with the following. I want us to look at v dot w. And why do I want to look at that? Well, just see what happens. What is v dot w equal to? It's going to be, of course, because v is v1 plus v2, this is v1 plus v2 dot w, which is equal to v1 dot w plus v2 dot with w. But this one is 0. And it's 0 from right here. Now, v1 dot vw is the same thing as alpha w dot w, right? From here, just replacing v1 with alpha dot w. Now, alpha is something that we basically want to know. If we can find alpha, then we will know v1 because we know w. If we can then find alpha, then we'll have solved for v1 because v1 is alpha times something we know, w. Since we know v and w both, we actually have an equation with only one unknown. v dot w is equal to alpha w dot w, which, by the way, is the same thing as alpha times the magnitude of w squared. So what I'm going to do is I'm going to divide both sides of this equation by the magnitude of w. And then I end up with alpha is equal to, and sorry, that's squared, is equal to v dot w over the magnitude of w squared, which means that v1 is v dot with w over w's magnitude squared, and then from here w, right? That's alpha times w. This is the v1. And to get v2, simply look back at this. If you know v1 and you know v is going to be v minus v1. Just move this to the other side here. And there you go. You have now taken v and turned it into how much of its vector or force or whatever it's representing is moving in the w direction and how much of it is moving orthogonal to it. You can find that with these two formulas. Now I've written it out for you. So you've got the two formulas here and here. And let's do an example where we actually decompose these for two given vectors. So in order to do this, to find v1, we need to know v dot w. v dot w is going to be negative 3 times 2 plus 2 times 1. Multiply the x components, the y components, and add them up. That's negative 6 plus 2, or negative 4. We need to know the magnitude of w squared. That's simply 2 squared plus 1 squared. That's the x value of w squared and the y value of w squared, which is going to be 4 plus 1, or a 5. So v1 is negative 4 from here, this formula, over 5 times w, 2I plus j, which is negative 8/5 I minus 4/5 j. And v2 is v minus v1, or negative 3I plus 2j minus negative 8/5 I minus 4/5 j. That's negative 3 plus 8/5 times the I plus a 2, and then minus times a minus makes plus 4/5 j. Negative 3 is negative 15 over 5, so that gives me a 7/5 I, and this is going to be 10 over 5, so it gives me plus 14/5 j. And that's how we find the two vectors that are the decomposition of v into the direction of w and a direction orthogonal to w. What should be true is if you add V1 plus V2, you had better get V, right? If you add negative 8/5 to 7/5, you had better get negative 3, which I don't, so I did something wrong. This is negative right here, right? So you get negative here. There's my error. Good thing that I checked this. Negative 8 plus negative 7 is negative 15/5 I, which is a negative 3I. If I add negative 4/5 to a 14/5 J, I get a 10/5 J, or 2J. Negative 3I plus 2J is in fact V. So this checks out. I can confirm that these two, this and this are the decomposition of V into the W direction and orthogonal to W direction. There you go. That is the dot